Great to see you here again. I want to start this presentation, this short video, with a short message, because when you see this message, it means that this video is not edited. I couldn't edit it the way I would like to, and the quality may be less than what you're expecting from me, like on the other videos. So later I will restore it, but at this moment it is like it is, but it will help you to study the topic. Great to see you here again. Now we are in the fourth part of lesson 3, and we're talking about the principles of linear programming. Linear programming will be the last method that I will introduce here that will help you evaluate projects, make decisions, and find the best ways to do things. Let's have a look at the background of linear programming. Linear programming is basically a mathematical method based on linear inequalities, and we find this theory of linear inequalities already in mathematics, and we have typically equations of the form ax plus by larger or equal than c, or ax plus by smaller and equal than c. These are constraints that we are going to use. For example, a budget is limited to a certain amount. We have to have a minimum amount of production. So these equations represent business-related constraints. Now, the parameters a, b, and c are constants, and x and y are the variables. For example, we are comparing two different products. X and y may be the amount of those typical products that we are considering. So when you're looking at a budget and you're buying handbags, you can say that A and B is the price of one specific handbag, and X and Y are the number of handbags that we consider from a specific brand. Don't be afraid, ladies. I sometimes have people say, can we only have 2 handbags? No, it can be a lot more. Also for selecting cars, for the boys, no problem, there can be a lot more. But when we look at the theory, it's better to explain it with only 2 variables, because we can draw this on a piece of paper. It's only 2-dimensional. More dimensions are possible. We will talk about it later. But basically, the thing is that when we have more variables, it becomes more complex. Like I said, the 2 variables, we can look at more variables. Cars, shoes, handbags, computers, whatever we consider, and we can say basically that this is a very interesting system, and it reduces calculations dramatically. When we look at the solutions of this, now these systems were already discussed and resolved by Fourier in the 19th century. Now practical applications were only developed in the 1930s. You can imagine that calculations in the 19th century without any computers would have been very difficult to do, certainly when you have a very large number of possible solutions. Nevertheless, the method provides ways to simplify even that. Now, linear programming is very important in a lot of applications, project management, operations, decision making in general. But it's also very important to understand this, because sometimes when people go for a job interview, they are shown or they are given a problem to resolve, and that problem in many cases can be resolved using linear programming. Once you see that this is a problem that has those restrictions, that has a kind of optimization rule, then you probably can use linear programming. Now, when we look at early applications, like we said, the first introduction was in 1939 by Leonid Kantorovich. It was in the time of the Second World War, and one of the applications here was to evaluate how could we find an optimal solution, let's say at the lowest cost, to create as many losses to the enemy as possible. It's unfortunate, but many of those techniques and those methods are in fact based or are being developed in the military. Now, like I said, at that time, the method was still considered as being a military secret. It was only applied by a limited number of people, but later it became more popular and it became a basis for the application of linear programming in business. And there was also what we call the simplex method. It's basically a matrix-based method which provides a way to resolve this. I didn't include that in this course because this is going a little bit further. Today we have other possibilities. For example, you can use Solver in Excel. It's a method, it's an add-on to Excel where you can define linear programming problems, and it will help you to even resolve more complex solutions, and it's using basically the simplex method. Now, the first real problem, the proof of concept, was used to allocate 70 people to 70 jobs, which would be very, very difficult, extremely difficult, certainly at the time they were doing this, to do with the classical means. Basically, the simplex method and the linear programming method was helping the people to resolve this problem and to optimize it. Today, it's being used in many situations. When we look at the linear programming, we also have to see that we consider the general concept of mathematics based on those linear inequalities. So first of all, we have to consider certain elements. We can only use the linear programming method when the problem can be expressed in a linear form. When it cannot be expressed in a linear form, we cannot use linear programming, which is quite logical. Finite number of equations with a finite number of variables. So there can be a very large number of variables and number of equations, but it will be a finite number, not infinite. The combination of all these elements results in a closed zone or feasibility zone. I will show you. The feasibility zone is basically that zone where all the possible solutions can be found. Outside of the feasibility zone, we cannot have a solution. There are more than one optimization condition, so there we can have more conditions. If there is only one, then it's not really the goal to do, let's say, linear programming, because all possibilities will be possible. We have as a solution real numbers. Now, in certain cases, we also will have integers, but that's a special concept where we talk about integer programming. When you're producing cars, you cannot have a real number, you have to have integers. But also the solution, let's say, provides this. We look at the general solution here where we consider real numbers, but integer programming also is, let's say, existing and is used in many occasions. We look at a method to resolve it. So we have a simplex method, we can have a computer method. For two-dimensional problems, we can, for example, consider a graphical solution. We also have either a maximization or a minimization problem. We try to maximize a profit, for example, or we try to minimize production cost. So we can say we have different solutions. I have a shop, I'm selling different things, and we try to find the best combination to have the highest profit possible. When I am producing certain materials or certain products, I want to find a combination where my production costs are minimum. So all these things are in fact possible, maximization or minimization problem. Now, there is also what we call an objective function, and the objective function expresses the profit or the cost of the solution. And here we have more uncertainty related to the parameters, because when we look at all the constraints, these constraints are typically internal, our budget, our production capacity and things like that. But when we look at the objective function, we try to estimate the profit of the solutions, of the solution. And basically, this can be different than, this can be changing, and we have to be sure that we know those parameters with sufficient certainty. Now we look at the linear equations. We start with the linear equation. Basically, it's the start of linear inequalities and of linear programming. Now we have that linear equation, and when we look at it, and when you remember mathematics, we can identify the equation of a line based on congruent triangles. On other elements, we can define the slope of the line. All those formulas exist, and we can create the general expression of the line, typically given by ax plus b equal y. We also can find what we call the point slope expression, which is y is equal to mx plus k, with m the slope and k the y-intercept. So basically, these things you've seen in college algebra, and if you are not really used to do that anymore, it's been some time since you did it, it may be good to review some elements about the linear algebra. Now, when we look at the mathematical concept of linear inequalities, we have linear inequalities which are of this form. So basically, we have the inequalities smaller than a parameter. We can have a large number of expressions that can be smaller or equal than a value, or large or equal than a value. So basically, there are two elements that we have. Typically, for a budget, we will use the first form because we cannot exceed the budget. For the second element, we can say that we have to use a certain amount of raw materials, that we have to use more than a certain parameter that we decide in the production process. Now, the parameters ai, bi are the coefficients. They are given. These are the elements from our production, internal parameters typically, and xi are the variables. These are the different products that we are using, the different elements that we may be producing. Now, the number of variables can be large but finite, and the coefficients ai are given, and bi is the condition to comply with. So we have to have our budget. We have to spend less than our budget, so bi would be the budget. Now, when we look at it mathematically, we can say that the linear inequalities can have any values, but we will see that later when we use them in linear programming, there are some additional rules, but we will talk about that later. It's first that we have a look how we deal with this, how it works, and how we find those different solutions. Now, there is also some comments to make about the inequalities. And when we look at the inequalities, we see that we have smaller than or equal to, larger than or equal to, but we can also have larger than or smaller than. Now, typically in the expressions that we have, and most of the examples I've been working with, I always found that the equality sign is included. And when we draw a line and we say the equation ax plus by is smaller or equal than c, it means also that the points on the line itself are included in the solution. Also, with the larger than or equal, we have that element, and it's important to see, because if the lines are not included, it means that we have to be careful what values we select. Now, the first thing to do is to find the inequality, or to draw the inequality, to find the zone that is compliant with the inequality. And let's have a look by a simple expression. 2x plus 3y is smaller or equal than 6. So we cannot draw an inequality, so we have to work in different steps. First of all, we have to draw the line 3x plus 2y equal to 6, and then we have to find that, or we can find that line by using the x and y intercept. So we have the x and y plane. We only have two variables here. We find the first and the second intercept. The y-intercept is 0, 2, and the x-intercept is 3, 0. And since the definition of a line, we can draw this line through these 2 points. The next thing is to identify the inequality, and we evaluate 1 point. We take 1 point below or above the line. In this case, we have the point 0, 0, which is a logical choice because it's easy to calculate. And we see that 2 times 0 plus 3 times 0 is equal to 0. Means that in the point 0, 0, the linear inequality is positive. So basically 0, 0 is part of the feasibility zone of the half plane that complies with this condition. So now we can draw that half plane, and this is in fact the entire zone of points x and y which comply with the inequality. Now let's have a look at the general problem and look at the number of inequalities. I have 4 inequalities. I don't give you the details, just a qualitative example. Now for practical use, we keep the variables to 2, and it's very easy to represent the feasibility zone in an x and y diagram. Basically, we can draw it on paper, and it's very easy to show to you. We can have more equations, we can have more variables, but be sure that it becomes more and more complicated, certainly when we have more and more variables. These are the elements that we have to do, and we have to comply with these conditions. Now, creating the feasibility zone is the first thing to do. So we look at the feasibility zone, which gives all combinations, all variables that comply with all inequalities. So we have a set of different inequalities given in the graph, and we always draw the line and the zone that is included. So we find always the zone, and we see that we have overlapping zones. At first we had only the zone below the purple line. Now we have the orange line, and we see that the zone between the 2 lines to the left is in fact compliant with both equations. We have another one, and we see that the zone is getting limited. And the last one gives us here a closed zone, the darkest zone, where we find basically the feasibility zone. And this is what we want to find. We want to find this zone, and all the elements in that zone, including the corner points, are basically possible solutions that comply with all inequalities. Now we look at some constraints and the objective function. Now we look at problems resolving issues that include limited resources, and we want to find the best utilization over these resources. The type of problems are typically maximization and minimization problems. We have a limitation of resources, for example, budget, storage space, and others, and they are expressed as a series of constraints of this form. So we have the smaller or equal to bi, or larger and equal to bi. On the other hand, we must find an optimal solution, which is expressed by what we call the objective function, and we have a maximization or a minimization. Now the parameters C1 up to Cn here, when we have a maximization problem, these are typically related to profit, while when we have a minimization problem, these are related to cost. It is clear to state that when we want to optimize, maximize profit, we basically want to have a value of the objective function which is as high as possible. We want to maximize it. When we have a minimization problem, we want to minimize the cost. Now, when we look at linear programming, I spoke about additional conditions that we have to take into account. For mathematical explanations, all those values x and y can be any value, can be real numbers, can be integers, can be negative, can be positive, and so on. Now, when we look at linear programming, we have to add some more conditions. A first condition is the non-negativity condition. Now, we always have to say that the values of xi, the values always have to be positive or equal to 0. We can produce nothing, but we cannot produce negative amounts. So basically we have to see that when we find a solution, that those solutions are positive. And these elements are typically not described when we describe a linear programming problem. When we describe a linear programming problem, we don't mention this condition. This is a condition that we have to add in order to have a linear programming problem following the rules. The objective function, there is only one objective function expressing either profit or cost. That's also very important. And the parameters in the linear inequalities are certain. It means that we have the knowledge, these are elements from our own organization, and we know the cost to produce, we know the budget, we know the elements, we know the surface. So these are certain parameters that we have. Although for the objective functions, that's not necessarily certain. And we can see what is the flexibility, what is the elasticity of the solution, but we will not do that in this part of the course. Let's have a look at a problem to resolve. We have the following information and we want to have a linear programming method to find the optimal solution. So typically we have this solution. It says, consider a factory in which we are producing two types of bicycles, fancy and sporty. In order to produce the bicycles, we have two types of processes. Process 1 is in fact the process where we prepare of the separate parts, and process 2 is the assembly of the bicycle. The team 1 works on process 1, has a capacity of 1,440 hours, and the team 2 has a capacity of 600 hours. Process 1 takes 6 hours for the fancy and 4.5 hours for sporty. Process 2 takes 3 hours for fancy and 1.5 hours for sporty. We do not want to have more than 300 sporty and 175 fancy bikes in stock. The profit on sporty is 100 and for fancy 165. And here we have to determine the optimal mix. So basically we have to look at the different processes here. We know that process 1 is the preparation of the separate parts. The team 1, which works on process 1, has a capacity of 1,440 hours, 6 hours for one fancy bike and 4.5 hours for one sporty bike. So these are the elements for the first constraint that we have here. We are looking at the constraint of team 1 when they are producing different combination of bicycles. The second thing is process 2. So we look at the same thing. We look at the assembly of the bicycle. Team 2 has a capacity of 600 hours. Yes, and 3 hours for fancy and 1.5 hours for sporty. The last thing we have to find is we do not want to have more than 300 sporty and 175 fancy bikes in stock. So basically we found the constraints in this description, and now we have to find out what is the objective function. And the objective function here is given by the profit on sporty is 100 and for fancy it's 165. And now we can start writing the constraints. Now we put everything in a table, we work in a structured way, so we find all the different elements. Sporty is variable X, fancy is variable Y, and we have the different processes here. So basically for process 1 we can say that the expression becomes 4.5x plus 6 times y smaller or equal than 1,440 hours. That's just saying when I'm applying process 1, I have not more than 1,440 hours. I know that for x for sporty we need 4.5 hours, for fancy we need 6 hours, and the combination of the two gives in fact that first equation. We do the same for process 2. And here we find 1.5x plus 3y has to be smaller or equal than 600. We still have the maximization here, the maximum conditions for sporty. So x has to be smaller or equal than 300. Then we have for fancy where y has to be smaller or equal than 175. And here we have all the constraints, and on the bottom I add the non-negativity constraints, basically saying that x and y have to be positive. The objective function we got from the description, the profit on sport is 100 and for fancy 165. So we can say 100x plus 165 is maximum. And that's in fact the equation that we're going to maximize. Now we have to draw this. So we have our x and y table. You may have to have some practical experience to draw this in a good way. When you're using programs, it can be a lot easier. Of course, you can only draw when we only have 2 dimensions. So we have the first equation. We find the x and the y and intercept. We have those 2 intercepts. And we can draw the line through it. So that's basically the line. We have the line here and smaller or equal than 1440. So the part below is the feasibility part. Now I draw it in a different color. I draw it in the opposite side because now the feasibility zone will be very easy to recognize because it will be a wide zone. And when we did it in the other way, it becomes the darkest zone, and it can be a little bit more difficult to find when you have a lot of colors. You have all kinds of shades of gray, and you have to find out which is the real zone. But like this, I do it in the other way. So I color the non-feasible part. We do for the next equation, 1.5x plus 3y smaller or equal than 0. We also draw the different intercept. We have the y-intercept. We have the x-intercept. We have the y-intercept. And we combine those in the graph. And basically, these are the elements that we have to foresee when we are drawing these graphs. Again, we select the zone which is basically not compatible. So we have everything under the orange line, and that gives us the possibility to find already a less restricted zone. But we still have some conditions to add. X has to be smaller or equal than 300. So we put a vertical line there. We also, everything that's larger than 300 is not accepted. We put the other condition, y is smaller or equal than 175. So we have this line additionally here. And now we see a zone. It's the zone, the white zone below, but there's still something missing. And what is missing is at this stage, we still can have negative solutions. So we have to add the non-negativity conditions. X and y have to be larger or equal than 0. And now we see the complete feasibility zone, which is the white zone between all those curves. And of course, any point within this zone, including on the lines, is in fact a possible solution. Now, when we look at this, we can have different ways to do it. We can draw the objective function, and we can draw it as a line through 0, 0. Here we have profit 0. So basically, when we draw this line, this is an equi-profit line. All the points on this line have the same profit. Now here we have only one point within the zone. So we move further, and we try to go as far away from the point of origin, and the perpendicular distance between the origin and the line, the farthest away from the origin is in fact the solution, the optimal solution. And we see that we have the intersection point between the orange and the red line is the farthest way. This is the last point of the feasibility zone. Now, if the slope of the objective function is different, you will find, or you can find, a different point. All depends on the two parameters that we have selected, and this is basically for our solution. This is the equi-profit line for different combinations. The next thing we can do is, in fact, going, and we see the point here 160/120 when we do the calculation, when we calculate the intersection here, that's basically the solution. But we also have a different way of doing that. We can find all the different intersection points. We have all those intersection points. Some have already been drawn before. I added some extra ones here, and we see that we can have solutions in 0, 0, 0, 175, 50, 175, 160, 120, 315, and the last one is 300. And this is basically the start of the way to use the corner point method. And the corner point method means that we put everything in a table, and we see that we have the different coordinates, the coordinates of the different corner points, and we calculate for every corner point the value of the objective function. So basically for 0, 0, that's easy. It's 0. For 0 and 175 is 28.8 thousand, and so on. So we find that for all the possible solutions, and we select the maximum value, which corresponds with the corner point 160/120, with a profit of 35,800. Now the thing is here, when we look at these elements, this is the solution for a maximization problem. When we have a minimization problem, we have similar exercises, but basically what happens is that we have something in the other direction. We try to minimize the objective function. So here we have to be careful. I had sometimes students on an exam, they had the minimization problem and they resolved it as a maximization problem. Of course, the solution was wrong, but it's a very, let's say, a mistake that can be made rather quickly. But we have the maximization problem here. We also can have a minimization problem. A lot of interesting things that will help you, that will give you tools to apply in many, many cases, not only in project management, but that's basically the advantage of project management. You're combining so much knowledge, so much elements from different disciplines. Basically, as a project manager, you're kind of an octopus with not 8 arms, but a lot more arms, because you have to deal with all those different elements all the time. So that was it for this presentation. I'm looking forward to seeing you, and the next time we will be talking will be lesson 4. So thank you and bye-bye.